Good morning, everyone. Hope you are all doing fine. Today we shall discuss the phenomena of aromaticity. What are aromatic compounds? Why are they different from any compound that we have dealt with before? Let's first look at the first aromatic compound that we have ever seen. When we say an aromatic compound, the first structure that comes to your mind is the benzene ring. Why is that? Because this is the first compound that has drawn our attention to the phenomena of aromaticity. Organic compounds are classified into aliphatic compounds and aromatic compounds. What is the difference between both aliphatic and aromatic compounds? Aliphatic compounds are the classes of compounds that we have dealt with up till now. They are compounds that have group of carbons attached to each other, either by single or double or triple bonds, and they have functional groups attached to them. So what are aromatic compounds? These are ring structures. They have to include a ring in their structure. They are compounds that have ring and they have unsaturation within this ring, and still, despite the presence of this unsaturation, or despite the presence of double bonds in their structure, they still react by substitution reaction. If you remember, when we were discussing the aliphatic compounds, we discussed the alkanes, which are totally saturated compounds, and we said that these react by substitution reactions. But when we discussed the alkenes and the alkynes, which are compounds that are unsaturated and they contain pi bonds, we said that they react mainly by addition reaction. If you take a look at the benzene, which was the first example of aromatic compounds that drew our attention to this strange phenomena, you will find that the compound contains 3 double bonds. And even though it contains 3 double bonds, if you try to perform any of the reactions that can be done by alkenes or can be done on alkenes, you will find that the benzene ring will not be able to perform such reactions. Examples of which are whenever you try to add a water molecule to an alkane in presence of an acid medium, you will end up with the alcohol compound. Try to perform the same reaction on benzene and you will get a negative reaction. If you have an alkene and you add a hydrogen halide molecule to it, you will end up with the alkyl halide. However, if you perform the same reaction on benzene, you will get a negative reaction. Again, if you have an alkene and you reacted with potassium permanganate, you will get the diol. If you try the same reaction on benzene, you will get a negative reaction. Finally, if you take an alkene and you reacted with halogen in presence of carbon tetrachloride, you will get a dihalide compound, a vicinal dihalide compound. Running the same reaction on benzene using the same conditions will give a negative reaction. However, if you perform this same reaction using a Lewis acid on the benzene ring, you will get a reaction, but not what you expect. What you expected was that one of the double bonds will break open, and you will have 2 halogens attached. So you are actually expecting this product. However, you will not get this product, and the halogen will be introduced in place of one of the hydrogens. One of the hydrogens will be removed and the halogen will replace it. So it's a substitution reaction. So this type of reaction drew our attention to the strange phenomena of aromaticity. So, as we have mentioned, Organic compounds are classified into aliphatic and aromatic compounds. Aliphatic compounds are compounds that either are saturated or unsaturated, and if they are saturated, they will react with substitution. If they are unsaturated, they will react with addition. However, the aromatic compounds are compounds that react with substitution even though they are totally unsaturated compounds. The first example of aromatic compounds known to humanity was the benzene molecule, where its general formula is CnH2n-6, giving the C6H6 compound. It's a six-membered ring containing 3 double bonds. This is how it looks like, and it's a planar compound. What is highly characteristic of the benzene is that, as we said, it does not perform any of the reactions of the alkene compounds, even though it contains 3 double bonds. As you can see, potassium permanganate will give no reaction. Hydration will give no reaction. Halogenation will give no reaction except if we use Lewis acid, and the product will be a substitution rather than an addition product. The positions of the double bonds of the benzene is not known. None of these bonds is really a single nor a double bond. This bond is partial single, partial double. The same applies for this bond. It's a partial single, partial double. There's a continuous resonance moving the double bonds and the single bonds between the positions of the ring, and accordingly we do not know the positions of these double bonds. This can be proven by measuring the bond length of these bonds. You will notice that they are all of the same length, even though some of them should be single, some should be double, and as you know, single bonds are longer than double bonds. However, if you measure the length of these bonds, you will find that they are all of the same length, and this length is in between the single and the double bond length. It will be in the middle, in between both lengths of the bonds. Why is that? Because if you look at the six-membered ring, it will have 6 p orbitals. Each one of these carbons is an sp2 carbon having a py orbital perpendicular on the plane of the ring, as you can see here, and the electrons are moving in an electron cloud above the ring and electron cloud below the ring, as you can see, and the ring is in between in the form of a planar or a flat structure. This is how benzene really looks like. So, how do we decide whether a compound is aromatic or not? So that when we are designing a reaction, we would know how it will react, whether it will react using an addition reaction or a substitution reaction. Just being a ring is not enough. Just having double bonds within this ring is not enough to say that a compound is aromatic or not. They have to be present. You have to have the ring and you have to have a group of double bonds within this ring. However, this is not enough. You have to have additional requirements to say that your compound is an aromatic compound. These requirements are 4 requirements. The first is that all the carbons inside the ring should be sp2 carbons. This will definitely lead to the fact that the structure should be planar. If all your carbons are sp2 carbons, then your structure should be planar. This is usually fulfilled by a conjugated compound or a compound that has a continuous resonance. So as you can see, the first 3 requirements are prerequisites to each other. Each one of them leads to the other one. If one is satisfied, most probably the other 2 will be satisfied. And then we have a 4th requirement, which is a little bit away or different from the 3 others, which is what we call Huckel's rule for aromaticity. Huckel's rules say that 4n plus 2 equals pi electrons. In this equation, you have an unknown, which is the n. The pi electrons are not unknown. They can be calculated from the structure that you have. You have to use this equation to calculate the n. If your n is a fraction, then this is not an aromatic compound. And if your n is an integer, integer means it's a whole number, whether 0, 1, 2, 3, or so on, then your compound is aromatic. Let's apply this to a group of examples. Let's first look at the benzene structure. Let's look at each carbon. Is this carbon an sp2 carbon? Yes, it has a pi bond attached to it, so it's an sp2 carbon. The same applies here. The same applies to this carbon, that carbon, that carbon, and that carbon. So all 6 carbons are sp2 carbons. So this is the first requirement. This will lead to a planar structure, so all are sp2. This will lead to the fact that it is a planar structure, and as you can see, a resonance exists. You have, what is a resonance? You have to have a conjugation. What is a conjugation? A conjugation is an alternation between single and double bonds. As you can see here, you have a double followed by single, double, single, double, single, and so on. So you actually have a resonating structure where electrons are moving within the ring. So the resonance, continuous resonance exists. So check, check, check. What we have left is the Huckel's rule. As we said, Huckel's rule says that 4n plus 2 equals the number of pi electrons. How can we calculate, or how can we determine the number of pi electrons? Usually a double bond is 2 pi electrons. You can calculate, or you can consider a pi bond to be 2 pi electrons. And a negative charge, so a pi bond equals 2 pi electrons. A negative charge again is equal to 2 pi electrons. A positive charge is equal to 0 electrons. 0 pi electrons. Why is that? A pi bond is a bond between two sp2 carbons. Each one of them has a p orbital containing 1 electron. So this is why we calculated by 2 pi electrons. A negative charge means that this atom has its own electron in addition to an electron that has been given to it by an atom that left the structure. So it has 2 pi electrons. A positive charge is an atom that has no electrons or has 1 electron less. The outermost shell electron that was used in a certain bond was taken by the atom that left the structure. So now it is not carrying any electrons. It's just carrying a positive charge. A charged carbon, whether carrying a positive charge or a negative charge, is considered as an sp2 hybridized carbon. So let's apply this to benzene. How many double bonds do you have? You have 3 double bonds. 1, 2, 3. So 3 double bonds, each one it consists of 2 electrons, so these are 6 electrons. So 4n plus 2 equals 6. So 4n equals 4, so the n equals 1. It's an integer, so this is an aromatic compound. Let's apply this to other examples. If you have the naphthalene, a naphthalene is a compound having 2 benzene rings fused to each other. Let's first look at the first 3 requirements. Let's look at all carbons. This carbon is an sp2 carbon. It has a pi bond attached to it. sp2 carbon, 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 sp2 carbon. So all carbons are sp2. Accordingly, this compound is planar. Let's look at the resonance. You have a double, single, double, single, double, single, double, single, double, single. Some of you will say that we have two single bonds following each other. If you move this way, this is a double, single, double, single, single. So you might consider this to be breaking the continuity of the resonance, which is not true. It's still a conjugated compound and it has continuous resonance. Why is that? You have another root which you can use to fulfill the continuity of the resonance. Where is that? You have double, single, double, single, double. You do not have to move this way, move that way. It will give you a double, and then a single, and then a double, and then a single, and then a double, and then a single, and then move this way. It's a double, and then single. You do not have to go the way that has two single bonds following each other. You have another root that fulfills the continuities, so use it. When do you say that this compound does not have continuous resonance? When there are no roots that can fulfill the conjugation of the structure or the continuity of the resonance. If you have this single and single and you do not have a double here that can solve the problem. In this case, you will consider that this is not a conjugated compound and it does not have a continuous resonance. So this compound does have a continuous resonance. Let's apply Huckel's rule. It says for n plus 2 equals pi electrons. Let's calculate the pi electrons. You have 1, 2, 3, 4, 5 double bonds. So 5 multiplied by 2 equals 10 electrons. So the 4n equals 8. So the n equals 2. It's an integer. So this is an aromatic compound. Let's apply this to something like anthracene. So again, all carbons are sp2. If you just follow them in the structure, you will find that they are all sp2. The compound is planar. You have continuous resonance. You have double, single, double, single. Do not move this way, move that way. It's double, single, double, single, double, double, single, double, single, double, single, double, single, double, single, double. You can keep moving. If you can always find a single followed by a double, followed by a single, followed by a double in any of the roots, then this is a conjugated compound. So the first 3 requirements are fulfilled. Let's go to the fourth one, which is the Huckel's rule. 4n plus 2 equals the pi electrons. Let's calculate the pi electrons. We have 1, 2, 3, 4, 5, 6, and 7 pi bonds, which means that we have 14 electrons. So 4n equals 12, so the n equals 3. So this is an aromatic compound. Let's again apply to phenanthrene. So if you go through all the carbons, you will find that they are all sp2 carbons. All these are sp2 carbons, so your compound is planar and the resonance exists. Let's look at Huckel's rule. 4n plus 2 equals, again, 7 pi bonds, so it means 14 electrons. So the 4n equals 3, so the 4n equals 12, so the n equals 3. Let's apply to other rings. For example, a cyclobutadiene. All carbons are sp2 carbons. So requirement number 1, check. So it will be a planar compound and the resonance is continuous. Let's apply Huckel's rule. 4n plus 2 equals pi electrons. So 4n plus 2 equals 4 electrons. We have 2 double bonds, each of 2 electrons. So 4n equals 2, so the n equals half, so it's not an aromatic compound. Let's apply to cyclopentane diene. cyclopentadiene, you will have sp2 carbon, sp2 carbon, sp2 carbon, sp2 carbon, and this is an sp3 carbon. So rule number 1, or requirement number 1, is not fulfilled. Accordingly, planarity is not fulfilled. Accordingly, a resonance, as you can see, you have single followed by single, and there's no other route that can solve this problem, so resonance is not solved. Finally, Huckel's rule, 4n plus 2 equals 4 electrons, so the 4n equals 2, so the n equals half. Again, Huckel's rule is not fulfilled. Let's place a charge on this compound. Let's try to place a negative charge, and let's try to place a positive charge on the same structure. In case of placing the negative charge, all carbons now are sp2. We said that a charged carbon is an sp2 carbon, so all carbons are sp2. So rule number 1, check. Planarity will be fulfilled because all carbons are sp2 carbons. Resonance exists because the negative charge will complete the resonance, so resonance is fulfilled. Huckel's rule says that 4n plus 2 equals pi electrons. We have 2 double bonds, each of 2 electrons, so this is 4 electrons, and we have a negative charge that has 2 electrons, so these are 6 electrons. 4n plus 2 equals 6, so 4n equals 4, so the n equals 1. So just by placing a negative charge on the cyclopentadiene, you have changed it from a non-aromatic compound to an aromatic compound. Let's apply the same for the positive charge. You will find that all carbons are sp2. The planarity exists and the resonance exists because the positive charge will complete the resonance. So all 3 rules exist. Now for Huckel's rule, 4n plus 2 equals 4 electrons. We have said that the positive charge is devoid of any electrons. It does not contain any electrons. So you only have the 2 double bonds. So it's 4n plus 2 equals 4. So the 4n equals 2. So the n equals half. So this is not an aromatic compound, even though it fulfilled the previous 3 requirements. Let's apply the same to something like cycloheptadiene. Cycloheptatriene. You have a 7-membered structure. You have double bonds in this structure, 3 double bonds in this structure. However, you have this sp3 carbon. So sp2 is not true, and planarity is not true, it's not fulfilled, and the resonance is not fulfilled. However, if you apply Huckel's rule, you will find that this compound has 6 pi electrons, so your n will be equal to 1. Still, the compound is not aromatic because it did not fulfill one of the 4 requirements. Let's place a positive charge and a negative charge on this structure. Once you have placed the negative charge or the positive charge, you have changed all carbons to sp2 carbons, and accordingly, in both compounds, you have fulfilled the first 3 requirements. Remaining the Huckel rule to be applied. In the first structure, where you have the negative charge, you have 1, 2, 3 double bonds, each of 2 electrons, meaning you have 6 pi electrons, and you have the negative charge having 2 electrons, so these are 8 electrons. So the 4n equals 6, the n equals 3 over 2. It's not an integer, so this is not an aromatic compound, even though it fulfilled the previous 3 requirements. Let's apply the same for the positive charge. 4n plus 2 equals, you have only 3 double bonds, 1, 2, 3, while the positive charge is devoid of any electrons, so you have 6 electrons, so the 4n equals 4 and the n equals 1. It's an integer, so you are fulfilling Huckel's rule, and this is an aromatic compound. So as we have mentioned, to be an aromatic compound, a compound has to fulfill 4 different requirements: planarity, all carbons are sp2 hybridized, continuous resonance, and Huckel's rule. Huckel's rule, 4n plus 2 equals pi electrons. We applied this to naphthalene, to cyclopentane, diene, to anthracene, phenanthrene, cyclobutadiene, and the anions of a non-aromatic compound like the cyclopentadiene and the cycloheptatriene. The anion of the pentadiene is aromatic, even though the starting compound is not. However, if we place a positive charge, it will not be aromatic. On the other hand, the heptatriene, if we put a positive charge, it will be aromatic, while if we put a negative charge, it will not be an aromatic compound. Now, discussing the nomenclature of these compounds, we usually consider the benzene as the parent, except in certain cases that we will discuss. So your parent is benzene, and whatever is on this benzene are just substituents. So if you have here a chloro, this is a chlorobenzene. If you have a nitro group, this is a nitrobenzene, and so on. We have some common names that we will look on the slides that are organized. But first, let's discuss the di-substituted and the tri-substituted benzenes. If we have 2 substituents on the ring, say for example a halogen here and an amino group there, then you have 2 substituents and you have to determine their positions. Let's first start with a simple example: 2 chloro groups. First, you have to decide which structure is your parent. Your parent structure is the benzene. You have 2 substituents on the benzene. If you start numbering here, then this goes 1 and 2, then this is the 1,2 dichlorobenzene. Definitely you will move in this direction to give the substituents the least possible numbering. This is the EUPAC way of nomenclating such a compound. However, if you try to nomenclate it in a common way, it will be called the ortho dichlorobenzene. What is the meaning of the ortho? If you have a benzene and you have a substituent on this benzene, you have 3 positions to relate to if you are nomenclating in a common way. You have the ortho positions, you have the meta positions, and you have the para positions. The ortho are the ones directly following the carbon that is having the substituent, the ones that are directly adjacent or immediately adjacent to the carbon that is carrying the substituent. The meta are the ones that follows by 1 carbon. You leave 1 empty carbon and then you place your substituent. This is the meta. And the para is the one on a straight line from your substituent. Let's apply this to such a structure. Where is the ortho positions? The ortho positions are the ones that are directly adjacent to the carbon carrying the Z. So these are the ortho. The meta are the ones that follows. You have to leave 1 carbon empty and then jump to the next carbon. This is the meta. And finally, the para is the straight line substituent, the substituent present on a straight line from the Z. If we have 3 substituents on the benzene ring, you cannot use the ortho-para system. However, you use the 1, 2, 3 system for nomenclating. Let's look at the slides that explains such rules and shows how we can nomenclate these compounds. As we have mentioned, we have the mono-substituted compounds. We just name the benzene and the substituent, and the benzene is the parent compound. Then we have the common names of some very popular and very common aromatic compounds. These are the toluene, where you have a benzene carrying a methyl group. You have the benzene carrying a hydroxyl group. This is a phenol. You have the benzene ring carrying an amino group. This is the aniline. You have the benzene carrying an ethylene group. This is the styrene. The benzene carrying a methoxy group. This is the anisole. The benzene carrying an acetyl group. This is the acetophenol. The benzene carrying a carboxylic group. This is the benzoic acid. The benzene carrying a sulfonic group. This is the benzene sulfonic acid. You have to realize that these names are just common names. They have no rule. They have to be memorized. You cannot just understand a certain system for naming them. These are common names. They have no reason. You have to memorize the names. And please notice that there will be no exam devoid of such a question. Usually, whenever you are being examined in aromaticity, you will be asked to nominate some common names of certain compounds. You will be faced by some structures and you will be asked to give in their common names, or you will be given some common names and you will be asked to give their structures. The di-substituted compounds, as we have mentioned, will be named either in the common way using the ortho, meta, or para nomenclature, or you can name them in the EUPAC way by using the numbers, which is the 1, 2, 3, 4, 5, and 6. These are the positions of the benzene ring. We have one more common name, which is the xylene. The xylene is a benzene ring carrying two methyl groups. If they are in the ortho positions to each other, this is the ortho-xylene. If we skip one carbon, then this is the meta-xylene. If they are on the same straight line, then this is the para-xylene. Finally, the tri-substituted compounds. These are named regularly. This is the benzene, and then you can give numbers to the different substituents starting from the highest priority functional group and giving numbers to the other groups. Here the anisole is the parent of your structure. The anisole is the benzene carrying the methoxy group, and then you will number to give the fluoro and the ethyl the least possible numbering. If you number in this direction, you will have the ethyl as 1, 2, 3, 4, and you will have the fluoro as the 6, 5, 6. While if you number in this direction, you will have the fluoro as the 2 and the ethyl again as the 4. So you choose the number in this direction. Again, here you have the toluene, which is the benzene carrying the methyl group, and it has in the 2, 4, and 6 positions the nitro group. Now, suppose you have on the benzene ring two groups, for example, a methyl group and another group that has higher priority than the methyl. For example, well, I cannot think of a certain example now. Any other group that has higher priority. Suppose a chloro group, for example. So, how do we name this? This is benzene. So, will we say that this is carbon number 1, 2, 3, and then we have the chlorobenzene having a methyl group at the 3 position? Can we name it this way? No. This is totally incorrect nomenclature. Why is that? We have an exception to the numbering system. When we are considering the highest priority functional group, we have to first, in case of aromatic compounds, First, look at the possibility of joining the benzene with one of its substituents in one name. For example, if you join the benzene with the methyl, you will have the toluene. So instead of saying methylbenzene, you will say toluene. You are decreasing the name of the structure by one entity. You are decreasing it. You're converting two names, two components, the methyl part and the benzene part, into just one component, which is the toluene. In this case, the toluene will be the parent of your compound, and then it will be the 3-chlorotoluene. You will have to consider the group that, when combined with the benzene, gives a certain name composed of one component. You will have to give it a higher priority to decrease the number of components of the name of your structure. Okay, if both substituents will not fulfill such a requirement, will not give a simple name, then you will go back to the regular priorities. If both substituents will have different names, for example, something like that, if you have the amino with the benzene, this is aniline, and if you have the carboxylic group with the benzene, this is benzoic acid. So both have a one component name. In this case, you will go back to the rules of priorities, and this will be the amino benzoic acid, because the carboxylic group has a higher priority than the amino group. So priorities are considered in a very systematic way, in the same way that they are considered in aliphatic compounds, except in one case, which is if you have one of the substituents, if combined with the benzene ring, will have a common name of its own. So you will not have to mention it as a separate substituent on the benzene. In this case, you will give this a higher priority than the other functional groups or the other substituents present on the benzene. One last point before we leave the topic of nomenclature of aromatic compounds, which is the exceptions for considering the benzene as our parent structure. As we have mentioned, whenever you have a structure containing benzene and different substituents, you will consider the benzene as the parent, and then you will place all the other substituents as prefix at the beginning of the name, because they are just substituents on the benzene. However, we have three cases where we consider the benzene as a substituent. And if we consider the benzene as a substituent, it will be called the phenyl group. So it will be phenyl on something else. What are these three exceptions? The first exception is if you have a side chain attached to the benzene that contains carbons, more than 6 carbons. So if you have a carbon chain more than 6 carbons attached to the benzene, this chain will be your parent structure. Looking here at this, you have 1, 2, 3, 4, 5, 6, 7. So this is the heptane. And on carbon number 1 of the heptane, you have a phenyl substituent. This is the first exception. The second exception is that if you have a cycloalkane attached to your benzene, even if this cycloalkane is only 2 or 3 carbons, let's use the cyclopropane for example. You have only 3 carbons. This is the smallest cycloalkane that you can think of. So this is going to be the cyclopropane. This is your parent. And then on carbon number 1 of the cyclopropane, you have a phenyl substituent. So this is the second exception. The third exception is if you have a side chain on the benzene that contains a functional group. For example, if you have an amino group on the side chain, even if this side chain is just 1 carbon, still it will be your parent compound. So this is the methane amine, and it has a phenyl substituent. If you have two carbons, this is the ethanol. You have two carbons having an OH. This is the ethanol. And then on carbon number 2, you have a phenyl substituent. So as we said, the three exceptions are if the side chain is longer than 6 carbons, if the side chain is a cycloalkane, no matter how long is this cycloalkane, even if it's only 3 carbon, or if your side chain contains a functional group, even if it's just 1 carbon, still it will be the parent, and the benzene will be a substituent on this parent structure. So as we have said, these are the exceptions. If you have a chain having more than 6 carbons, if you have a cycloalkane of any number of carbons, regardless of the number of carbons, if you have a side chain containing a functional group, regardless of the number of carbons present in the side chain, still the side chain will be the parent compound. Now moving to the reactions of aromatic compounds, these can be classified into electrophilic substitution reactions and nucleophilic substitution reactions. As we said, aromatic compounds do not react by addition, they only react by substitution, either electrophilic or nucleophilic. In case of electrophilic substitution reactions, you will have the attacking reagent as an electrophile. In case of nucleophilic, your reagent will be a nucleophile. The nucleophilic reactions are rare, and they take place only if the benzene has a very strong electron withdrawing group on the ring, on the nucleus. However, the electrophilic substitution reactions are the most common, and they are mainly 4 types of substitutions. These are the nitration, sulfonation, halogenation, and the Friedel-Crafts, whether alkylation or acylation. Let's look at all types of electrophilic substitution reactions. How does an electrophilic substitution reaction on benzene take place? It takes place through several steps. First of all, you have to form your electrophile from your reagent. We will postpone this till the end of the mechanism. Let's look then after the formation of the electrophile. Now you have the benzene. The benzene is an electron reservoir. It contains a lot of electrons. The electrophile is something that needs electrons, so the benzene will attack the electrophile, placing it on the ring. Now you have the electrophile, you have the hydrogen of the benzene, and you have the positive charge on this carbon. Why did this carbon carry a positive charge? You had a double bond. The electrons of the double bond accumulated on this carbon, leaving this carbon with no electrons. So now it's carrying a positive charge, and this carbon carried for a moment a negative charge with which it attacked the electrophile to produce the reaction. Now we have a resonance, stabilization of the positive charge. How does resonance proceed? In resonance, you have 3 atoms together, 2 of which are having a double bond in between, and the third one is having a charge, whether this charge is a positive charge or a negative charge. In the resonance, the double bond moves from one side to the other, and the charge moves from atom 1 to atom 3. So now this one will carry the positive charge. This is just to simplify. What actually happens is that we have 1 carbon here carrying a positive charge, which means that it needs electrons. So the carbon adjacent to it will attract both electrons of the double bond. It will pull them towards itself to form a double bond with the carbon divide of electrons, placing a positive charge on the carbon that was already bonded to this carbon. This is how a resonance will take place. Let's apply this to benzene. So now you have, this is your 1, 2, 3 system. Let's apply this to it. The electrophile is in its place, the hydrogen is in its place, this double bond has not been touched. Now we move the positive charge from atom 1 to atom 3, so this is the place of the positive charge, and we move the double bond from its position to the single bond. We exchange the single with the double bond. So this was double, it will be a single, and this was single, it will be a double bond. Let's perform the next resonance. Again, where are our atoms? This is 1, 2, and 3. Let's perform the resonance. This double bond was not touched. Now the positive charge has been moved from 1 to 3, so this is the position of the positive charge, and an exchange of the single with the double. So this now becomes a single bond, and this becomes a double bond. This is the second step of the reaction. The final step is that the hydrogen will leave as a proton to retain the aromaticity and give the substituted benzene. So this is how the mechanism takes place. We say that the positive charge was carried within the ring. It's not carried by a single carbon of the ring, it's carried by all the ring. This is the this is the arene structure, or the resonating structure. We consider this to be, we say that this is the arenium ion, or the delta complex. This is the resonating hybrid of the benzene. Now let's go back to the formation of the electrophile. As we have said, we have 4 types of reactions. The nitration. In the nitration, we use conc nitric acid in presence of conc sulfuric acid. The sulfuric acid here is just a catalyst. What happens is that you have the nitric acid. This is the structure of nitric acid, the correct structure of nitric acid. So you have an oxygen here that carries lone pair of electrons. It will be protonated in the acid medium, removing a molecule of water, giving the nitronium ion. This is the electrophile that will be attacked by the benzene, the nitronium ion. It will be attacked by the benzene, and then you will continue the mechanism of this reaction. And again, you will have the resonance, and you will fulfill the rest of the mechanism. Let's perform the halogenation. In this reaction, you have the halogen, and you have a Lewis acid. The Lewis acid has a vacant orbital, and the halogen has a lone pair of electrons. They will be donated within the vacant orbital, giving the Lewis acid in the form of an anion, and leaving the halogen, the second halogen atom, as a halonium ion that will be attacked by the benzene, giving your structure, which will be stabilized by resonance, giving the final product. The third reaction is the sulfonation reaction, and you do not need in this reaction to form your electrophile, because the conc sulfuric acid that you will use contains your electrophile. The conc sulfuric acid exists in a resonance between the sulfur trioxide gas, the protonated water, and the bisulfate moiety. The sulfur trioxide gas is your electrophile. What happens here is that your benzene will attack the sulfur trioxide, which can be drawn in this form, breaking one of the double bonds between the sulfur and the oxygen. So now your product is the sulfur having a double bond O and a double bond O and a single bond to a negatively charged oxygen. Now you will have the resonance. as we have studied before, another resonating structure. And then finally the proton will leave, and this proton will go and attach itself to this oxygen, negatively charged oxygen, giving the benzene carrying the SO3H. This is when you always ask, where did the hydrogen come from? This is the structure. This is where the hydrogen came from. This is the hydrogen of the benzene ring. You had an O carrying a negative charge. A proton left the benzene ring. They attached it to each other to give you the sulfonic group. Finally, the fourth reaction, which is the Friedel-Crafts reaction. This is divided into two types of reaction. It's either the alkylation and the acylation of the benzene ring. In case of the alkylation, you start with an alkyl halide, you add a Lewis acid to this alkyl halide. Again, the Lewis acid will have a vacant orbital, so the halogen will donate its electron in this vacant orbital, giving the alkonium, which is a very unstable electrophile. It's a weak electrophile that will be attacked by the benzene, giving the alkylated benzene. Following the mechanism first to finally give the alkylated benzene. As for the acylation, you will have an acyl halide, This is an acyl group, acid having a halogen, and again you will use the Lewis acid. It will have a vacant orbital. The lone pair of electrons of the halogen will be donated, giving the acylium. However, the acylium is a stable moiety because it is stabilized by resonance of the oxygen, where the positive charge can be carried on the carbon and can be carried on the oxygen of the acylium. Again, the benzene will attack this acylium to give the acetyl or the acyl benzene. So these are the different electrophilic substitution reactions that can be performed by the benzene ring. The nitration, the sulfonation, the halogenation, and the two Friedel-Crafts reactions. So now, looking at the general mechanism of electrophilic aromatic substitution reactions, we will notice, as we have mentioned, that the benzene will attack the electrophile, giving the resonating structure, the resonance hybrid, the arenium ion, and then finally the proton will leave to retain the aromaticity. We say that we are retaining the aromaticity of the structure. As we have mentioned, you can have halogenation to produce the halonium, nitration, where your electrophile will be the nitronium, sulfonation, where your electrophile will be the sulfur trioxide, Friedel-Crafts alkylation, you will have the alkonium, which is a very weak electrophile and unstable electrophile. You will have the acylium, which is a stable because it is stabilized by resonance, as we have mentioned. These are examples of the Friedel-Crafts acylation. Now we have some limitations to the Friedel-Crafts. Only the Friedel-Crafts will show these limitations. We have 5 limitations to the Friedel-Crafts reaction. What are these limitations? The first limitation is that you can have polyalkylation. I will start with the easy ones and then move to the more difficult ones. What is the polyalkylation limitation of Friedel-Crafts? If you are performing an alkylation reaction of the benzene, you are using the alkyl halide in presence of a Lewis acid. So you will have the alkonium, and it will be attacked by the benzene, and you will produce the toluene. The second alkonium group now have 2 choices to be attacked with. It can be attacked by a free benzene that has not reacted yet, or it can be attacked by the toluene. The alkonium group is an electrophile. It is looking for electrons. The benzene has electrons, but the toluene has more electrons because the methyl group is an electron donating group by induction. So the toluene will be preferable. It has more electrons in its ring. So the following product will be the dimethyl, the xylene. It will not proceed towards using all the benzene molecules to give the toluene as a final product. On the contrary, it will leave some of the benzene unreacted and it will go to the toluene to produce the xylene, and it can further react with the xylene, which will have more electrons because now it has two electron donating groups to give the trimethyl compounds, and it can give the tetramethyl compound, and that's why we say that this is a polyalkylation limitation. I will not get the pure toluene, I will get polyalkylated benzene. So this is the first limitation. The second limitation is that strong electron withdrawing groups on the ring will limit this reaction. For example, nitrobenzene, if reacted with alkyl halides in presence of Lewis acids, will give a negative reaction. Strong electron withdrawing groups like the nitro group, like the carboxylic group, like the acyl group, like the sulfonic group, these groups withdraw the electrons of the ring towards themselves, rendering the ring not having sufficient electrons to attack a weak electrophile such as the alkonium group. So strong electron withdrawing groups on the ring will not perform Friedel-Crafts alkylation reactions. The third limitation is if you have a group on the ring that is having lone pair of electrons like the amino group or the hydroxyl group. These groups, if reacted with the Lewis acid, they will donate their lone pair of electrons in the vacant orbital of the Lewis acid, giving the positively charged substituent on the ring. If I am using aluminium halide or Lewis acid in small amounts, then I will not be able to perform the Friedel-Crafts alkylation. I will get a negative reaction. However, if I use excess amount of Lewis acid, I will still have some of the Lewis acid unreacted with the aniline or the phenol. The problem is that your substituent is using the vacant orbital of the Lewis acid, so it's actually destroying your catalyst, and it's not available now for the halogen of the alkyl halide to react with to produce the alkonium, so you are getting a negative reaction. You can add excess amount of the Lewis acid to overcome this problem. This way, when all the amino group or the hydroxyl group have reacted with the aluminum chloride, you will still have some free aluminum chloride to react with your alkyl halide. In this case, you will still get the alkonium, and the alkonium will be attacked by the ring. However, when you reacted the amino or the hydroxy compound, you were expecting the substituents to go to certain positions which are related to the positions of the electron donating groups. When you have an electron donating group, and this is going to be discussed in full details, when you have an electron donating group on the ring and then you substitute by another substituent, the substituent usually goes to the ortho and para positions. However, in this case, you will not get the ortho and para substituent because your amino group now does not have a lone pair of electrons on it. On the contrary, it has a positive charge. So now it's an electron withdrawing group, and accordingly it will direct your substituent to the meta position. So instead you will get the meta alkyl aniline rather than the ortho or the para alkyl aniline. When you have an electron withdrawing group on the ring, it directs the second substituent to the meta position. When you have an electron donating group on the ring, it directs your substituent to the ortho and para substituent, and we will discuss this in full details in a following video. The fourth limitation is the vinyl group and the phenyl group. If you need to react these in presence of a Lewis acid with benzene to substitute it, for example, if you are trying to synthesize the styrene, your mind will first think of reacting benzene with the vinyl halide to produce the styrene. The halogen will go away, it will react with the Lewis acid, giving the styrene as giving the ethylene as a positively charged moiety that will be attacked by the benzene. But this is a totally wrong way of thinking. Why is that? If you remember in the video of alkyl halides, we have mentioned that in the vinyl case, you have the halogen directly attached to a double bond, so you have the p orbitals of the vinyl in the same plane parallel to the halogen, and you have an electron cloud above and electron cloud below. So this bond is not really a single bond, it's a partial single, partial double, so it cannot be broken by any reagents. So this reaction cannot proceed. The same applies to the phenyl halide. This is your vinyl part. If you look carefully at this part, you will find that this is a vinyl. You have a carbon doubly bonded to each other, and the halogen is directly attached to the vinyl moiety. So again, if you are trying to synthesize this structure, you cannot simply use the phenyl halide to substitute the benzene. This is another limitation of Friedel-Crafts. Now, the final limitation of Friedel-Crafts is the rearrangement. If you are trying to synthesize this compound, your first thought will be to react benzene with propyl halide in presence of Lewis acid to give you the propyl benzene. This is a totally wrong way of thinking to produce this required structure. Why is that? As we have mentioned, when you react this alkyl halide with the Lewis acid, what will happen is that the halogen will donate its electrons to the vacant orbital, producing the carbocation of the alkyl group. If you look at this carbocation, you will find that it's a primary carbocation. What happens here is that one of the hydrogens of the adjacent carbon will be shifted. You will have a hydride shift to produce the more stable carbocation. Now, this is the carbon that will be attacked by the benzene, and instead of getting this product, you will actually get this product. So you will not get a straight chain compound on the benzene. Whenever you are using any alkyl group, one, two, three, four, five, you will always get one of them out as a methyl. It will produce, if you put the positive charge here, one of the hydrogens will be shifted, so this will be the methyl on the other side, and then the rest of the chain. You will always get the methyl substituent of the chain -1 carbon. So if I actually need this straight chain compound, I do not want the branched form of the compound, I need the straight chain. How can I get it? The best way to get such a compound is to acylate. If you remember, we said that the acylium is a stable carbocation. So you use an acyl halide rather than an alkyl halide. In this case, when the halogen leaves, putting a positive charge on the acylium, it will be a stable acylium. So now you have the acylated benzene, which is not what you want. What you want is the alkylated benzene. However, you can reduce this using either Clemmensen reduction, using mercury, zinc, mercury, and HCl. This is one way. And the second method is the Wolff-Kishner reduction, where you use sodium hydroxide and hydrazine. In both cases, you will reduce the doubly bonded oxygen to a CH2. So these are the these are the 5 limitations that can face you while performing Friedel-Crafts alkylation reactions. So again, your limitations are the rearrangement. You will get the iso compound, or you will get a secondary carbocation giving a branched structure, and we have solved this using the acylium rather than the alkonium, and then reduction using the Clemmensen or the Wolff-Kishner. Strong electron withdrawing groups will not allow Friedel-Crafts reaction to take place, and accordingly they will give a negative Friedel-Crafts reaction. If you have an amino or a hydroxy group on the benzene, it will react with the Lewis acid, destroying it, so you will get a negative reaction. And if you increase the amount of the Lewis acid, you will get your product in the meta rather than the ortho and para position. The phenyl and the vinyl will not react, and you have the problem of the polyalkylation reaction. This is the end of this video. The di-substitution of the benzene, the introduction of a second electrophile to a substituted benzene ring, together with the introduction of a third substitution, and the different derivatives of benzene will be discussed in a video that follows this one, in a part 2 of the aromaticity video.